Hello again, everybody. Thank you very much for joining us. My name is Irina, and I'm very happy today to announce a tinyML meetup. Before introducing our guest, first of all, I would like to introduce my colleague, Francesco Paci, who brings a wealth of experience in working on low-power applications. And today we will be discussing noise, keyword spotting in a noise environment. Before starting our presentation, as usual, I want to express our appreciation to our sponsors, AIZip, Arduino, ARM, BrainChip, AgeImpulse, Fish and Green Waste Technology, Groovity Incorporated, HiMax, Imagimob, Infineon, Inatura, Nota AI, NXP, PNG, PMIC, Pollen Technology, Qualcomm, Renesas, Schneider Electric, SensiML, Sony, Silicon Labs, ST, Synaptics, Syntian, TDK. To mention for those who is not aware that we have a huge community of tinyML, it's a tinyML meetup. Please follow this link and subscribe, and also tinyML community on LinkedIn. Don't forget to check YouTube channel. This video will be recorded and uploaded in a couple days there. A couple words about upcoming events. You can check the Tiny AI forum on anomaly detection. It's going to take place in December in I think Pacific time, so in States. Also, tinyML Research Symposium, April 22nd, and tinyML Summit, same date, take place, the same in States in Burlingame. Don't forget, there is an Age AI technology report available at this link. Francesca, I will give you this floor now to introduce our special guest, please.
Thank you, Irina. And yeah, I have the pleasure today to welcome Cristian Cioflan, which would give today's talk at the tinyML Talks webcast. So Cristian received his bachelor degree from the University of Bucharest in electrical engineering and information technologies, and then his master degree in ETH Zürich, where he is now pursuing a PhD with Professor Luca Benini on digital circuits and system group. And his research interests include audio processing in low power embedded system, neural architecture search for energy efficient learning, and on-device continual learning. So thank you, Cristian, to be here, and I leave you the floor.
Thank you, Francesco, Irina. I hope you can hear me well. I hope you can also see my screen. Welcome, everyone. Thanks for joining us today. Good morning, good afternoon, good evening, depending on your time zone and the place you're listening from. And let's take a dive into on-device domain adaptation for noise-robust keyword spotting. We can start by discussing what keyword spotting represents, giving a definition to it. It's an AI or machine learning branch, depending how you want to see it. We can consider it that we start by processing an audio signal, and then we want to recognize a word from that spoken utterance, a word belonging to a predefined set. And we might want to do this in order to control embedded devices, whether we might want to turn loud our cochlear implant, or take a photo with our smart glasses, or why not control a drone remotely. Now, one specific setup for keyword spotting would be that from the input, we process it by extracting the male frequency sectoral coefficients, the relevant information from that audio input. Then we might pass it through a depthwise separable convolutional neural network, a network that is well known to be small enough in terms of parameters and computation, but powerful in terms of accuracy, such that in the end we recognize the keyword that has been pronounced by the target user. Now, if this is happening in silent environment, for instance, the meeting room in which I am right now, it is rather easy to perform keyword spotting. Even with this tiny neural network of around 20,000 parameters, we get more than 92% accuracy, and the state of the art now 99% accuracy, depending on the data sets. Now, the issue is What happens if we are in a noisy environment? If we are in a meeting room and if, I don't know, a hackathon is taking place somewhere, it might become significantly harder to predict that keyword that has been pronounced, that is being recorded with a microphone on an ultra low power system. In that case, that additive background, people chatting in the background, or I don't know, an ambulance passing by, will pollute our signal. And with SNRs going as low as -10 decibels, surely we will have troubles understanding what has been pronounced. For instance, here we can see an initial input that has been a person saying yes, but then it might be hard to recognize even visually that that signal, that yes, within the entire recording, which contains also noise. So in case we assume a noiseless keyword spotting model, a model that has been trained without any awareness of noise, will it still be able to recognize a keyword within the noisy environment? Well, in practice, we observe that there are accuracy drops, right? So let's have a look here on this plot. The same model, instead of when we analyze it on a silent environment, we see that it achieves, as we said, 92% accuracy. But then on the other hand, if we expose it to previously unseen noises, we see that the accuracy can drop largely. For instance, if we emulate a restaurant environment, we see accuracy drop of 52%. That renders the model de facto useless, right? This depends based on the type of the noise. If it's stationary or non-stationary, we might be able to recover more or less of the understanding. For instance, a washing machine has a noise profile rather predictable, so it's rather simple to still be able to record and predict our keyword. But then whether we speak about speech noise, people chatting in the background, we see 43% accuracy decrease at 0 decibels of an SNR. It becomes, as we said, really difficult to separate the target from the noise. Now, what simple thing we can do, and we have seen already this in computer vision when we pre-train a model with different brightnesses for the image, or we rotate the image during the pre-training stage, we can do the same here. We can augment the training samples with diverse noise types from various data sets. We can even augment it with noise of different SNRs, such that we emulate louder or softer environments. And surely we can improve the accuracy. We see increments between 10% for noises that were rather simple to bypass, washing machine, for instance, and significant increments, 34% for restaurants, as we saw before. This comes at the price. The famous English saying of jack of all trades, master of none, right? As we increase the accuracy on all the noises, we are not able to be specialized on one particular noise. In this context, for instance, on silence, we lose 4% accuracy. Now, what we want to try is to improve the keyword spotting accuracy through direct noise exposure and de facto becoming masters of some noises. Can we do this? Well, the reason I'm in front of you today is to tell you that yes, with on-device domain adaptation, we can improve the keyword spotting accuracy through direct noise exposure. How do we do this? Well, we start with a noise-aware keyword spotting system that has been pre-trained with several noises from different environments, and we deploy that on a microcontroller. We deploy not only the model, but we only take some pre-recorded utterances from the dataset with which we have trained our model. And this way, by having those pre-recorded utterances already labeled, we degrade our user from recording several utterances per class and having to label them, which is a rather tedious job. The third step is noise exposure. So that microcontroller, once deployed in the environment that is noisy, starts recording some on-site noise, a couple of seconds, and then that noise is used to pre-record, to augment the pre-recorded samples, which leads us to the on-device domain adaptation step, where we refine the noise-aware keyword spotting system using those augmented utterances. In practice, what we do is that, first of all, we combine the additive background noise, the meeting noise, for instance, with those pre-recorded samples that allow us to already have the ground truth, the label of that sample. We then compute the cross-entropy loss for our partially frozen module, and only some layers of the network will be updated based on the cost and the accuracy increment of that update. And then in the end, we should be able to increase the accuracy with our newly trained parameters. So the 5 steps to summarize would be that first we pre-train the noise aware. Then we deploy this model onto the target platform. We augment the utterances. This allows us to refine the network, and then we can recognize the keywords in that noisy environment. To model this ODDA for our experiments, we use Google Speech commands to represent our utterances. And for noises from different environments, we use the demand dataset. There are 18 noises in that dataset, and we used 5 leave one out settings. So, for instance, in the cafeteria setting, we trained our model on all the other 17 noises, and we test and perform ODDA only on cafeteria, the same for the other noises, considering SNRs between -10 and 10 decibels, such that we can verify whether we are capable of increasing the accuracy not only in simple environments when the noise is really far in the background, but also in somewhere there is a really loud noise source. So you might ask me, and if you're not, then I'm going to tell you anyway, how well does ODDA perform in these noisy settings? Well, let's first have a look at the qualitative analysis, right? We look here at our second to last layer in our neural network, and we do a visualization of the features in a 2D space. Basically, each point here is one sample from our test set, but augmented with the emitting noise. And as you can see, the samples belonging to 12 classes from the Google Speech commands. Those are 10 words, yes, no, up, down, left, right, on, off, stop, go, plus 2 special instances, 2 special classes. One is silence, which is the absence of any spoken word, and one is unknown, which is any other word that one might pronounce. And as you can see, for the noiseless keyword spotting model, we have quite a big mess, right? It's really hard to disentangle the samples belonging to each class, as the noise is really affecting those. And as we are moving from the noiseless keyword spotter to the noise aware one to ODDA, we see a better separation. In detail, for some of the classes, we see only marginal improvements. For instance, yes and stop, as we can see, have been pretty well separated in all 3 contexts, as phonetically they are rather different from the consonants with which they end, whether it's yes or down, or simply the vowels and the length of the vowels that comprises these words. On the other hand, when we have a large similarity between the keywords, for instance, off and on, which are fundamentally separated by the consonant in which they end, the fricative F and the palative N, in these two setups, we see a significantly better separation as we retrain our model with knowledge over the noise environment, as opposed to before, where there was, as I said, and as we observe here, really hard to disentangle the features. And sure, there are still limitations, as we see for no and go, for instance. There is still pretty difficult to separate, as they end in the same vowel, and they start with a rather similar consonant. So they are phonetically similar, and they are also short. In newer data sets, for instance, in the MSWC dataset, we see that already 2-character words have been ditched, and people are moving towards 3-character words for keyword spotting in order to bypass this effect of phonetically short words. Quantitatively, we see that ODDA offers accuracy improvements in any noise setting. So we see, compared to the noiseless keyword spotter, improvements between up to 37%, so significant increments compared to, for instance, the noiseless keyword spotter that we have started with, 37 on restaurant, 30% in the speech noise that we were observing before qualitatively. But even in the context where we were already pretty good at recognizing, so for instance, the washing machine, we still see an additional gain in accuracy. And this happens not only at 0 decibels, but this also happens throughout a wider range of SNRs between -10, so a really aggressive, really loud environment, and even 30 decibels, where one can assume that the noise should not be an issue. We see that the ODDA effect scales with the SNR. So the more you know about the environment, not only about the noise profile, but also the noise amplitude, the more you can gain. For instance, 5-6% in -10 decibels of an SNR. And we observe furthermore that when we do not have any knowledge about that particular environment. For instance, when we do ODDA with when we pre-train with an SNR between -10 and 10 decibels, in the test environment, a rather aggressive one, we have 10% accuracy increment over the original noise-aware QR spotter. Now, I will take a water break, and if you have any questions for now, let's try to answer them.
Yeah, we already have a couple of them. The first one was related to the choice of the keywords, and it's asking why you decided to not combine together silent and unknown, since they could be, I mean, the same. What you really bother is to recognize the keywords. So that's the first question. And the second one, which is probably linked to this, is what is, I mean, it's more related to where we use KWS in a real world. So the question is, so the model can recognize just 10 classes, and so in which real world situation you need them with relation to, for example, a wake up word like a Siri or any other else.
One good context for it, for keyword spotting, moving away from the simple wake up system of saying okay device, would be the drones example that I was giving in the beginning. So let's just say that you want to control a drone remotely, and you might want to follow the debris and go within a building that might have fallen due to an earthquake. And then you can have maybe a camera on that drone, and then you want to control the drone by simply saying up, down, or left, right, stop and go, or get closer. So you would want to be able to control that drone, or you want to be able to control your smart glasses. Just a couple of commands. For instance, just take a photo or start recording in case you're approaching what might be a dangerous situation, or simply turn off if you want to be in a really private setting. In this context, only a couple of commands to start the really simple default modes of your applications, of your systems, should be sufficient. On the other hand, you might want to trigger something more complex down the pipeline. And this might answer the very first question, which was the separation between silence and unknown, right? So let's just say that I start talking, and maybe I'm in a meeting. I might not want to fully start, I don't know, one of the applications that my camera can do or that my microphone can do, but I want to start taking notes. In that context, I want to know whether there is nothing being spoken. So there is what we call silence, right? The absence of any word, in which case I will simply not do anything down the pipeline, or whether there is something being spoken, but none of the predefined commands. And maybe on those, I want to simply transcribe them, or I want to perform ASR onto them and do some heavier tasks down the pipeline. In that case, there is some information that might, that could be processed, that might become relevant, but is not one of the target commands that trigger one specific or a different specific application.
I hope so. Yeah, but for me, yes, it does. And thank you. I have maybe a couple of others. So, I mean, there is one on the implementation, which I think, and the libraries, which I think we'll see in the next section of the presentation. And then there are two others. One is related on the amount of model parameters that you use in your experiments. And the second one is why in the results that you present with the ODDA, in silence condition, there is a drop. Okay, because we would expect that it should maintain the performance in the silence.
I'm gonna start with the first part, as it's a really quantitative answer. The examples I gave before, so the results measured before, were done with the DSCNN small, that is 19.2 thousand parameters. So 19,000 parameters. If you quantize it to int8, that's 19 kilobytes. It's a rather small model. We have experiments also done with DSCNN medium and large, and now we are scaling to more complex models. There we talk about 100,000 parameters, but that one there only 3 million operations and 19 kiloparameters. So really tiny, and yet powerful enough to achieve the 92% accuracy in silent conditions. Now, as you noticed, and this was a point I was addressing before, as we specialize on noise X, the accuracy decreases on silence. The reason is that in domain adaptation, as opposed to, let's say, continual learning, we want to specialize on one particular environment. As we move from one environment to another, we want to become extremely good in the present context, in the present setting. And we are willing to trade some accuracy in the context in which we were before, as we assume we will not be exposed to them again. And if that will be the case, then we can simply retrain. So as opposed to those contexts of continual learning where we might want to apply some regularization when we do this training, or we want to have some rehearsal-based learning to keep in mind some samples from the past, here in domain adaptation, we simply expose our model to the newest environment in which the microcontroller is placed, which leads to this accuracy drop in previous environments.
Okay, thank you. So we have other questions, but I think, I mean, we can go on with the presentation and then ask you at the end of it. Thank you.
Perfect. Let's do that. And let's actually move to the part addressing the actual implementation, as one of you was asking, right? So we are improving accuracy in the previously unseen noisy settings, but at what cost? What is the actual tiny machine learning cost to do this, right? We're talking about edge AI and rather extreme edge AI, right? Where we have miniaturized devices. I was talking about cochlear implants. So we have limited storage, which limits the number of model parameters, as one of you was pointing out before. You have limited memory. So the number of activations, gradients, again, parameters you need to use while computing your outputs is also limited. Second of all, I was mentioning drones, right? You need to be able to operate in real time such that you can not hinder the utilization of your drone. And this means that you need to have a really low latency, considering that you have a device with limited computational resources. And not only minimizing the latency, you want to also maximize the throughput, the amount of input samples that you're processing at once. And third of all, we are talking about battery operated devices, which are always on, which are always active. So you want to use low power or even ultra low power systems. For this context, we talk about resource constraint ODDA. And one aspect we might want to look at is the storage. And as we can see here, for three different models, also answering the question before, for DSCNN small, medium, and DSCNN large, the largest one comprising of 300,000 parameters, the smallest one, 20,000 parameters, we see that as we have access to more and more data, surely we can also increase the accuracy of the model deployed on that noisy environment. But luckily, you can have an accuracy improvement of more than 3% over the already noise-robust keyword spotting system by using only 310 samples per class, so 120 megabytes, which, considering that this should be stored in the flash, which is a rather cheap storage system, then that would still be affordable for the learning device. Second of all, as we assume that we are learning only once every maybe hours or maybe days as we are moving from one environment to another, surely having access to this data will not happen that often, and also the adaptation cost will not be incurred that often. Now, you might remember from before, as we were looking at the qualitative analysis, depending on the noise, we will have a different accuracy. And with meeting noise, which is a rather difficult noise, already having access to 3 megabytes of data, so that's around 10 samples per class, will lead to an accuracy increment of 5%, which is quite significant compared to an already noise-robust keyword spotter. Now, as we increase the model size, compared to the small one, we have additional 3.7% for the medium model, and then for the largest one, we gain 5% compared to the smallest that we have available. In terms of memory, as one would expect, depending on the depth of the adaptation, so depending on how many layers we will be updating from our neural network, surely we will have different accuracy impact. And once again, the amount of data we have available will correlate positively with the depth of the adaptation. What we observed is that for these points here that might not be that visible if you have a not so bright screen as I do at the moment, but on these points over here, we see plus 1.5%, so an accuracy improvement on average on all the noises compared to the already noise-aware QR spotting system by refining only the classifier, so only the last layer. And as we will see in a couple of slides, the classifier is rather tiny. This means that we need only 10 kilobytes of active memory, so parameters, activations, gradients, in order to be able to learn and to adapt to a previously unseen noise environment. To look at the model here, and to also understand a bit the precisions in which we are doing each operation, we start with our input, either a WAV from the Google Speech Commands dataset during the pre-training stage, or simply a recording of 1 second taken on the board. We then compute the MEL frequency crystal coefficients, and we do this in flow 16, as we see no significant accuracy loss compared to flow 32. Then the backbone of our network, the inference on the backbone of our network is done in int8, and we perform post-training quantization. And again, we observe no accuracy loss compared to the full precision model. So we get the advantages of SIMD, and we also get lower energy consumption while maintaining the performance, the classification performance. We do the quantization with Nemo, and we do the deployment with Dori. Both are open source tools developed in-house in ETH, in our lab IIS, in order to be able to deploy neural networks onto the parallel ultra-low power platforms. One example of those that we will see in 2 more slides. The last step, once we have the activations of our backbone, we dequantize them. So we go into FP32, and then with the classifier that is deployed in flow 32, we then perform inference, and we can also train this classifier. For this step, we use Pulp TrainLib, also open source tool. Everything is available for your use, and if you want to contribute to them, we will be more than happy. So with Pulp TrainLib, we deployed our fully connected layer, and we can also train it directly on the device. In more detail, we're talking about quite a small layer. As I was saying before, we have 64 input neurons, 10 output neurons, 12 output neurons, the 12 classes we were talking about before. So in total, 700 weights that we need to adapt. No biases here, as we saw no significant advantage in terms of accuracy. Also in Pulp TrainLib, we implement softmax and cross entropy loss, such that for the gradient computation, we have the full benefits of a high-level tool, but directly implemented in C and parallelizable over the cores. Over what cores, you might ask? Well, this is happening. Everything that you have seen before is happening on GAP9. This is a chip developed by Greenwaves from an original project that started in IIS. We are talking about 4 frequency domains. The advantage being that we can turn on and turn off each of these domains depending on our use to minimize the energy consumption. We are then talking about a hierarchical memory architecture. So from L3 to L2 to L1, with the data that is in L1 being accessible into a single cycle. And with our classifier being small enough that it fits completely in L1, it means that our entire training happens with the data directly there. So we win by the fact that we minimize the number of data transfers from the L2. And lastly, but by no means least, we're talking about the heterogeneous compute units. We have 10 RISC-V cores, one of them being the fabric controller, the other 9 representing our clusters. And in the cluster, it is where we parallelize not only the classifier, but also the entire backbone, allowing us for our depth-wise convolutional neural networks to achieve a latency that allows us to perform in real time with our QR spotter. Moreover, GAP9 has 4 FPUs on which we perform the pre-processing. So the MEL frequency crystal coefficients computation takes place with the FPU being utilized. Now, this GAP9 is being mounted on the GAP9 mode. The advantage of this being that apart from the chip, we have also an external RAM and external flash on which we are deploying our WAVs, our pre-recorded samples that, as I have mentioned before, are used to augment with the noise from the environment. And with those, we train our classifier or even more of the network, with the main advantage of not having to record samples and the user not having to actually label the sample themselves. Third of all, And this is a picture I have taken a few minutes before in my office. You can see the gap mod bit mounted here on the evaluation kit, and then together with the audio add-on. Here we have 4 PDM microphones. So we are using one of them for our experiments here, but surely one can use all 4 and maybe attack a beamforming direction from that point of view. And also it comprises of additional 2 DAC and amplifiers, such that one can also verify acoustically, so verify whether the input is understandable from a human point of view. Now, to understand a bit how our algorithm maps onto GAP9, we start by flashing the pre-recorded WAVs and also the model parameters, and for that we use the external flash on the gap mode. We then have the inference mode, so the setup in which we are simply classifying what is coming from a user. We have an always-on recording mode using the audio add-on microphones. Using the FPU, we compute the MFCCs, and then the backbone and the classification is being done directly on the cluster, benefiting from the distribution of the operations across the cores. For ODDA, we first record the on-site noise, and we use that to augment the pre-recorded samples that are being moved from the flash into the RAM. We then compute the MFCCs again, compute the intermediate activations at the end of the backbone. We then compute the classification output, but we don't stop there. We also compute the loss, and we update the classification parameters, leading to the accuracy improvement that we have noticed before. One example of this, a practical example in terms of usage in ultra-low power mode, assuming a frequency for the fabric controller and for the cluster of only 50 megahertz, and a voltage of 650 millivolts, we see that for a latency of only 50 milliseconds, which is basically how often we trigger the microcontroller, as the microphone, as in practice, by increasing the frequency, we would be able to run even faster with our inference. But assuming only 50 milliseconds of latency, we have an energy consumption of 1.3 millijoules. And the more interesting story, at least from this talk's point of view, right, the ODDA, so for learning directly on the device, we need less than one millijoule for the entire training. So for getting the data, augmenting it, computing the MFCCs, backbone inference, classifier, and update, for one sample, we need less than 1 millijoule. And in total, assuming that we use 10 samples for validation, so 1 sample per class, and then we measured the loss on those samples to see what is the pre-ODDA accuracy. Then we perform ODDA on 100 samples, that's 10 samples per class. And then in the end, we do again an evaluation to see whether the loss has decreased on those 10 classes. In total, the entire process takes less than 8 seconds and around 100 millijoules. Now, to conclude, with ODDA, we see that we can improve over NACUS by specializing on the target noise. We have accuracy increments up to 12% over the noise-aware QR spotter, assuming we work in the same data set on which we have done our initial pre-training, and we measure even 25% in case we expose our network to unseen data sets, and 37% accuracy increments over noiseless QR spotters at 0 decibels with a network that, as we said before, it's rather small, only 20,000 parameters. If we decrease the SNR to minus 10 decibels, we see 10% accuracy improvement over NACUS in all the settings. This comes at an inexpensive on-device learning cost, only 100 samples for plus 5% accuracy gain on meeting noise. And this requires as little as 10 kilobytes of active memory. And in the end, we can also demonstrate practical value on GAP9 with less than 1 millijoule per training epoch, and the total ODDA process, including the evaluation step, completing in 7.4 seconds, requiring as low as 100 millijoules. So thank you very much for your attention. And if there are any questions, I would be glad to entertain them once again.
Thank you very much, Cristian, for the talk. Yes, there are a few questions that popped up. And also, I mean, we have few which were there at the break that we took just before. Maybe we can start from there is the one which is asking I mean, whether the 10 or 15 or I mean the percentage that you have recovered with the ODDA, it's just if you can give a sense of if it's something that can be embedded in a product, so when you test it, beside I mean having numbers, it's something that could be ready to be let's say put inside the product. So what is your experience on this? And also, I mean, I think similar, but on the methodology that you use, there is another interesting question saying, I mean, what would be the trade-off if instead of doing on-device learning, you add a noise suppressor, a noise suppression network before the keyword spotter? So just to give an idea of the complexity or why did you choose this method?
Right. Thanks a lot. I will start with the second question. This is something we want to test as soon as possible. It's in the pipeline of our comparisons. The short answer is we have not tried to work with noise cancellation before the keyword spotter, and we rather took a completely different road of relearning the weights and basically recreating the projection planes for the intermediate activations in the presence of noise. The advantage, the fundamental advantage that I see in this context is that you do this adaptation once as you're moving into your noisy environment, and then you're able to do inference with a really low cost, as we have seen before. On the other hand, when we talk about noise suppression, you have basically a two-stage model. Every time you want to do keyword spotting or even ASR or more complex setups, you want to you have to always first do the noise suppression. So every time you consume energy for each iteration, which might be rather problematic in case you want to perform inference every few tens of milliseconds. It is a comparison we want to do in terms of energy and in terms of performance. But fundamentally, from a methodological point of view, we see this advantage of having the cost of the training spent only once and then being able to do only inference with a rather small model. Now, regarding the question, considering the industrial application of this, coming from a rather more academical point of view, I do not have much experience with respect to the industry. But what I have seen in the setup that I was showing before, right, with only 100 samples, so that setup that was finishing in less than 8 seconds, we were able to decrease the loss by 2 points from around 6 to around 4. Now, this doesn't say that much because when we use only 10 samples for validation, the accuracy in itself, as we do not have many samples to validate on, will not decrease percentage-wise. The quantile is too large. Our plan is to now increase the set of the validation that we use directly on the board and verify whether in an actual noisy environment with the microcontroller deployed there and with a few seconds of noise recorded used to augment the samples, whether we can do that in less than maybe 20-30 seconds. So yes, we do see a significant loss decrease, but I am not sure whether or how would that scale into the industry at the moment.
Okay, thank you. So I believe we have time for other few questions. Then please stop me, Irina, if we are out of time. So one is related to, I mean, the size when you deploy. So from one side you can have just the network, the noise aware one, and then when you need to retrain on device, you also add some size because you need all the libraries and the code related to retraining on device. So it is that if you can provide some information related to how much is what you add to a standard version of the let's say the noise aware with the relation to having on device learning, how big it is in terms of size of memory that you need to run it on device.
All right. So I would say the code size in itself is the list of the issues. The bigger problem, I would say, is first of all the fact that the classifier or the layers that you want to update need to be not anymore in int8 but rather in FP32. So already we're talking about a multiplication of a factor of 4, right? And considering also the activations and the gradients, as I was saying, for the memory, you need around 10 kilobytes only for the memory to update the classifier. Now, this is not an issue because already the backbone in itself, considering convolution with a feature map of 25 times 5 times 64, and each of them being bytes, we are already going to the power of 8 times 100, so that's already 25 kilobytes. So really, the limitation incurred by the classifier is not really a limitation, as in itself the memory for the backbone is larger. I would say the bottleneck is not really the model, and the bottleneck is not that you have to learn, so you need to modify the model when you're learning. The bottleneck at the moment are the samples you need to also have on your flash in order to be able to learn. So the limitation doesn't come at the on-chip memory, but rather in the transfer from the off-chip memory when you want to do this learning process. And here several approaches can be done. We are looking, as I was mentioning before, into approaches that have been tested in continual learning to see to what extent we can verify them in domain adaptation and we can apply them. But yeah, surely it is the pre-recorded samples that are the limitation, rather than the fact that we need to have the model or part of the model in 32 bits.
Okay, thank you. And then there are other two questions which I can group together. Let's say one is asking if you can actually target when you do on-device learning a specific user. So you can target the voice of a specific person. And the second one, which was a previous one, was more related to, let's say that since, I mean, the keyword spotter, this is something I didn't know. So it's mostly based on recordings which are done with webcam. So something which is not with a lot of quality. So whether you can recover this, and also you can also, I mean, work on modeling the differences between the microphones.
The second question is an absolute banger. Thank you very much for it. This is something that surprised us, and in the end, it makes a lot of sense. So you start with samples that have been recorded in really good conditions, either with microphones of I don't know, laptops, but we really tested with high quality concert microphones. What we can observe is that in ODDA, we can recover the microphone profile, and going from this high quality microphone to PDM ones with only a few milliwatts of power. So what we have done is, instead of considering a noisy environment, we consider the silent environment, right? So no noise around, where the noise is actually the difference between the microphone with which we have pre-recorded the samples and the microphone with which we perform ODDA. And in this setting as well, we observed a reduction in loss as the one we observed when we are in noisy environment. So really, we can, with ODDA, we can recover the difference in the microphone profile. This was not large. So from our experiments, around 5% of accuracy difference is observed between high quality microphones and really poor ones. But even that accuracy gap, we can recover with ODDA. Regarding the first question, this is really active research, so adapting to the speaker. In this with this ODDA, this might not be possible, as the goal here is to adapt to anything but the speaker. So either we are talking about additive noise, such as, I don't know, an ambulance in the background, or convolutional noise, for instance, the echo in the chamber you're recording from, and ODDA works well in this setting. We are now doing active research, and we have submitted a paper to ICSCP. Let's see what will be the output of that, towards adapting to the peculiarities of a particular user. So follow us, follow our lab, and surely research will come also on adapting to the speech characteristics of a certain user with his or her accent, with the pitch, and so on and so forth.
Okay, thank you. Thank you. Maybe just the last one, which was more related to, I coupled some of them, but let's say the question are, what happens if you move from the environment, which has a kind of noise to a kind of noise to another one? So let's say that if you also have done some tests, I mean, changing noise at runtime during retraining, or if they were just done, I mean, with a single noise, and what's happening when the environment is more dynamic than just with, for example, cafeteria, but when you change the noise, because, for example, you can have this with you, and so you're moving around and changing the noise which the device perceives.
That's a great question. The setup in which we consider we are functioning assumes that this change will not come that often, and as we can see, the energy consumption in that respect will be rather low. What we assume is that you would always start from the originally pre-trained noise-aware keyword spotting system, right? So since the bottleneck that you have at the moment is anyway on the number of samples you're storing, this means that additionally storing the original copy of your noise-aware keyword spotting system together with those samples does not lead to an increment in terms of flash required, which means that you're always starting from that pre-recorded model, then you're going to adapt to a target environment, and then when you're switching the environment, you're not starting from the previous model, but rather you're starting already from the original one. The test that you're mentioning is something that it's in our plan. So understanding whether this kind of incremental learning, so domain incremental learning, would work well, but we have not done them at the moment, as we have assumed a slightly different setup, a slightly different learning condition.
Thank you very much, Cristian. Let me just say that it was amazing presentation, very useful, I think, not from just academic perspective, but I see a lot of potential in the business industry, because this time in communicating with devices, users' voice, it's really getting a trend. So thank you, everybody. Let me finish today's presentation by just naming one more time the strategic partners. So it's Qualcomm AI Research, Syntian, Platinum strategic partners, AI Trios, and sorry about that. So ARM, Edge Impulse, Infineon, Inatura, Renesas, ST, Synaptics, and of course all these silver strategic partners: AI Zip, Arduino Brain Chip, Efficient Greenwaves Technologies, Groovity Incorporated, HiMax, Imagimob, Nota AI, NXP, PNG, PIMIC, Pollen Technology, Schneider Electric, SenseML, Silicon Labs, TDK. So thank you all for today's talks. Thank you again, Cristian and Francesco, and see you in the upcoming events. Take care.